Alright, ladies and gentlemen, this is the practice exam for acids and bases. This version might look a bit different than the one you have in front of you, because that probably is just reorganized numbers. I can't guarantee you this is the same exact version you have, because I just re-downloaded a copy online of our practice exam. And things might have gotten shuffled around. But anyway, it's still the same exact questions. Maybe it's a different order. I don't know. That's why I have that shrug icon there. It's my life. I don't know. Number 1. The electrical conductivity of an aqueous solution depends on the concentration of which particles in the solution. Alright, so this pretty much screams electrolytes, guys. Electrolytes in general pretty much compose of both strong acids and bases, or anything that dissociates into ions. Because acids and bases in general, when they dissolve in water, they dissociate into their ions. For the most part, strong ones do. Weaker ones, maybe not so much. Okay. So number 2. Given the equation representing a reaction at equilibrium, is that? According to one acid-base theory, so when they would explicitly say Arrhenius, they're telling you Bronsted-Lowry. So we gotta think acid-base conjugate pairs. Okay? So in this case, we're talking about the forward reaction. We gotta think about proton donors and acceptors. So here, we're always gonna have one acid and one base. So one of them is the proton donor and one of them is the proton acceptor. So we can't have both of these be the same thing. Now it's down to choice 2 and 3. One of them's got to be the donor, which is the acid, and one of them's got to be the acceptor, the base. So that's something to remember. And when we say proton, we mean H+, because that's essentially a proton. So looking at our two choices here, we got to clearly say that H2S, given that it has H's there in front, meaning that it's likely to give those up. That's the proton donor. So in this case, H2S is our acid. Hydrogen sulfide, by the way. And this right here is going to be our base. So we got to find the one that matches up. So choice 3 is the one that matches. H2S is a proton donor, because that's the acid, and CH3NH2 is a proton acceptor, because that's the base. Good. Now number 3 is another Bronsted-Lowry reference. According to one acid-base theory, the compound NH3 acts as a base because, again, we gotta look back at this phrase over here. The base is the proton acceptor. They accept the hydrogen ion. Good. Now let's change up the colors a bit. Number 4, the reaction of an Arrhenius acid with an Arrhenius base produces water and what? So we gotta think neutralization. Acid plus the base yields salt and water. You can't pick 1, 2, or 3. We didn't even talk about those. Those go on later in organic chemistry. So if you pick one of those 3, then you probably weren't paying attention, because we haven't even talked about those at all. Okay, but anyway, it's salt. Simple, straightforward, choice D. Number 5. According to one acid-base theory, a water molecule acts as an acid when the molecule, right over here, acts as a proton donor. Has to donate that H+. It's not going to be 2 or 3, because we're not dealing with OH-. We're only dealing with protons. Alright, now number 6. Phenolphthalein is pink in an aqueous solution having a pH of what? And bam! Here we go. I brought back table M. So here in table M, you're going to look at acid-base indicators. And here we're talking about phenolphthalein. That's what it says. That's how you pronounce it. It's a mouthful. I once had trouble saying that word. Anyway, so phenolphthalein is pink in an aqueous solution having a pH of, so we're looking right here, phenolphthalein. It changes between 8 and 9. And as long as you're above 9, then you're definitely pink. And the only one above 9 is 12. Everything else is below 8, which will remain colorless. Alright, number 7. What is the color of the indicator Thymol Blue in a solution that has a pH of 11? Thymol Blue is right here. And so if we have a pH of 11, we're way above the pH color change, the pH range for color change. And when you're above it, we're going to be blue. Okay, number 8. Oh, this is new. I've never seen something like this. Alright, here we have a diagram of a human body, 4 parts of the human digestive system. And they give us the various pH levels of certain parts of the body. And here you can see the stomach has the lowest pH, so that's super acidic. That's where most of the digestion occurs. Alright, what is the color of Thymol Blue at the pH of the small intestine? So let's add back our reference table M. So let me pull it out in a bit. It's coming up in a bit. Uploading, and here we go. And here we go. It's right here. Thymol Blue right here. Oh, ugh, I hate when that happens. Let's put in purple. I like purple. Thymol Blue. pH of small intestine is 7.3. We're below the range, so we're yellow. Based on the results of testing colorless solutions with indicators, which solution is most acidic? So let's go through each choice one by one. A solution in which phenolphthalein is pink. So it's got to be less than 8. Number 2. A solution in which Thymol Blue is blue. So that's below 6. So that already rules out 1. Number 3. A solution in which Cressel Green is blue. So that's above a 5.4. Can't be this one. A solution in which methyl orange is red. So it has to be less than 3.1. Alright, so that means below 3.1 could mean less numbers than below 6, and that means that can't be it, so we gotta be choice 4. The most acidic is the lowest number available. Number 10. Which change in the H plus ion concentration of an aqueous solution represents a decrease of 1 unit on the pH scale? So as we think about the pH scale going from 0 to 14, 14 being most acidic, to 14 being the most basic, if we decrease, we're becoming more acidic. And with more acidity, we have more H+, and because we have 1 unit difference leads to a factor of 10. So it's a 10-fold increase. Okay, so it can't be 2 or 4 because we're decreasing, and we got to think about how much 1 unit is. 1 unit equals a factor of 10. Alright, so that's a 10-fold increase. Number 11. The pH of a solution is 7. When acid is added to the solution, the hydronium ion concentration becomes 100 times greater. So hydronium ion concentration means H pluses, and it's going up. So that means we're becoming more acidic. And then 100 times greater means 2 units. So we are going down 2 units, okay, to become more acidic. Remember that 0 is the most acidity. We're going down. So going down from 7 minus 2 is a new pH of 5. Number 12. Here we are given a diagram to represent the equation reaction of HCl plus H2O to yield H3O plus and Cl minus. Here water is acting as the base. Why? Because we should already know HCl is a common acid. If you don't remember that, you can look it up on table K. HCl is definitely an acid. So that means it's definitely has to react with water as the base. Now, why is it a base? Do bases donate protons or do they accept it? So look what's happening to water. To become H3O plus, it had to accept a proton from over here. So that makes it the base. Why? Because it accepts a proton. Now number 13. Which acid and base react to form water and sodium sulfate? So if you don't know what sulfate is to begin with. Alright, so look here, I just brought up table K and table E, because you can use both to help you answer this question. So what is sulfate? You're going to look at table E, the polyatomic ions. Sulfate refers to SO4. So you're going to need something that is SO4. And how will that help you here? Because that'll help you determine the difference between sulfuric and sulfurous. So SO4 makes sulfuric. So that means we could cross off anything with sulfurous. So 3 and 4 are out. So sulfuric acid, which is H2SO4, and what? So we have here sodium. So we could combine it with sodium hydroxide. So that the Na and the SO4 make sodium sulfate. And the H2 and the OH will make more H2Os. And that is answer choice 1. There we go. Number 14. Which volume of 0.6 molar H2SO4 exactly neutralizes 100 milliliters of 0.3 barium hydroxide? So this is a titration question. So that means we're going to use MAVA equals MBVB. MAVA equals MIBVIB. Okay. So H2SO4 is our acid, and that is its molarity. So let's write off to the side here. Ma equals 0.6 molar. Exactly neutralizes 100 milliliters of that. Barium hydroxide is our base. Just to verify, H2SO4 is sulfuric acid from the previous question, so we should already acknowledge that's the acid. So that means barium hydroxide is our base. The molarity of that is 0.3 molar, and its volume is 100 mLs. We are looking for the volume of the acid. So we plug and chug, 0.6 molar times the volume of the acid equals 0.3 molar times 100 mLs. Solve 0.6 equals 30. And our volume of the acid will equal 50 mLs. Choice 3. Number 15. What are the products when potassium hydroxide reacts with hydrochloric acid? So this is a base and that's an acid. We should think they make salt and water. So water should be one of our choices. Nope. And nope to 2 and 4 because there's no water. So it's between 1 and 3. So that depends on the other guys. So potassium hydroxide is this. And hydrochloric acid is this. OH and H make water, so that means K and Cl have to make potassium chloride. Choice 1. Number 16. Which solution reacts with lithium hydroxide to produce a salt and water? So we're thinking that lithium hydroxide is a base. So we're looking for an acid. Choice 1 is a base, 3 is a salt, 4 is also a salt, so we gotta think that it's choice 2. Now moving on to number 17. It's another titration problem where we gotta calculate this. So use the equation again, but let's label our parts. This is our acid. So this is Va. This here is Vb. And this here is Mb. We're looking for Ma. Okay. You should get 0.8 molar, and that's choice 2. Number 18 is more titration questions. Okay, so number 18, here we got Thymol Blue is an indicator. Student titrates 15 milliliters of a sample of the vinegar, which is our acid. So Va equals 15 mLs with 43 milliliters of sodium hydroxide with a molarity of 0.3 molar. We are looking for the molarity of vinegar, Ma. So using the equation, MAVA equals MIBVIB, as I like to call it. You should get 0.862 molar as your answer for the molarity, and that's choice 3. Number 19, we need to figure out the hydrogen ion concentration of solution B. If it's pH of 5, then we just got to copy what it was for number 2. Okay, you take a look at the pH level, and it matches the negative exponent of the ion concentration. So here, solution A has a concentration of times 10 to the negative 2. Take away the negative of that exponent, and you get pH of 2. So following suit, it's going to be choice 3. Number 20, state the color of methyl orange in a sample of solution A. So methyl orange itself has a range of 3.1 to 4.4, if I'm remembering correctly. Maybe I'm a little off. So because our color changes from 3.1 to 4.4, the pH of 2 is already below the range. And here it's going to be red to yellow. Okay? It's strange that it's called methyl orange, but no orange color is involved. It goes from red to yellow straight on. Anyway, so since it's below it, it's got to be red color. And we finally reached the last page, okay, with all the free response questions. So number 21, we need to state how many times greater the hydronium ion concentration in the HCl is than the hydronium ion concentration in HC2H3O2. Okay, so we're comparing this and this. They differ by 1 pH unit. So that means it's a factor of 10. So we're already told that it's greater for HCl. So all we need to do is state the factor. So it's 10 times greater. That's all. Number 22. Determine the concentration of the HCl solution using the titration data. So we need to calculate this. Okay, so this is the acid. This is the base. MAVA equals MIBVIB. The molarity is what we're looking for of the acid. The volume is 25 milliliters. Molarity of the base is 0.15. And the volume is 18.5 right here. Plug and chug. And you get that the molarity is equal to 0.111 molar. Don't forget units, guys. Number 23, complete the equation for the neutralization reaction that occurs during the titration. Okay. So neutralization, we should think acid and base makes salt and water. So H2O is a given. And so the remaining ions make the salt, so it's KCl. That's it. Number 24. Again, we have to fill in the missing product. We already have H2O, so we just got to figure out what kind of salt is being made. And it's the same thing as 23, KCl. Number 25, we need to show a numerical setup for calculating the molarity of KOH. So this is a titration equation type of question, but we don't need to solve it. So we got here the acid data, and this is the base data. Okay. Got the equation, plug it in the numbers. Okay, so our numerical setup for finding molarity is going to equal to 0.026 times 50 divided by 38.5. I think an acceptable numerical setup is the substitution right here into the equation. I believe that's an acceptable numerical setup because you're essentially just rearranging things to make it look like this, so you could easily plug in one go and get the value. Alright, and that's that's it. 25 questions of the practice exam.